We will encounter a few times in this course the notion of functions being orthogonal to one another, and I want to spend a few minutes talking about what that means. Now, we've seen that this is true of different eigenfunctions of a Hermitian operator if they correspond to different eigenvalues, and we know that this functional orthogonality can be expressed sort of mathematically. If I have two functions f1 and f2 that span some range from a to b rather, that this integral is going to end up being equal to 0 if the functions are orthogonal to one another. But what does that really mean? I think the best way to view this is to illustrate it with a couple of examples. So I guess the first thing I would do is say that whenever we're taking the integral of any type of function, and let's say a is here and b is here, that this product of functions is going to be something that might look something like that. Actually, it's probably not going to look exactly like that because there's way too much area above the curve. But the whole idea is that all of the parts of this function that lie above the curve will contribute a positive contribution to the total area, and all of the parts of the function that are below the curve will contribute a negative. So if the total sum of the negative areas is equal to the total sum of the positive areas, that's when this overlap, this function integral, is going to vanish. All right, so that's what we're looking for. We're looking for a product of functions where we have as much area underneath the x-axis as we have above the x-axis. So let's see what this might look like in a couple of cases. All right, let's consider a first case where I'm going to have a pair of functions, and my first function is going to be just a Gaussian-like function. So that's f of 1 of x is just going to be e to the minus x squared. So it looks something like this. So this is 0 in this case, and so maybe this is minus a and this is plus a over here. And now what I want to do is multiply this times another function, which is just a line through here. So f of 2 is just going to be equal to x. Okay, so when x is negative, then we've got a negative points down here. When it's positive, it's up here. It's just a 45-degree line that runs through the plane. All right, now when I multiply these two functions together, it turns out I'm going to get something that looks like this. Okay, it's going to come down and then go up and then come down again like this. So when I go from minus a to plus a, I'm going to have a function that looks something like this, and this is the 0 point. So this is where the f of x equals x function is equal to 0, so when it multiplies this, even though it's at its peak, we're going to get a 0 out of that. So now if I look at this and just going to sort of visually scan it, I've got an area up here that's going to contribute a positive amount to the area, and I've got an area down here that's going to contribute a negative amount to the area. And I don't know if it's obvious to you, but because of the symmetry of this Gaussian function, this e to the minus x squared function, it turns out that these two areas are in fact equal. So in this particular case, I would have f of x1 and f2 of x. These are orthogonal functions, because when I multiply them together and then integrate from minus a to a of f1x, f2x dx, I should get 0. All right, so in essence what the orthogonality means is that the product is going to give me something like that. Now let's do this for a case that is maybe more closer to home, something that has to do with a system that we've already looked at. I have a particle in a box, and our box runs from 0 to L. And I know that the lowest eigenstate of this box is going to look something like this. Okay, it's basically sine of pi x over L. And the first excited eigenfunction is going to look like this. And I haven't drawn that very well, but it's going to go basically through the middle here. It's going to go through 0. All right, now if I multiply these two things together, I'll end up with a function that looks like this. and again I got to mark where L is located here because we can't go beyond L, we'll end up with a function that actually has a shape that looks more or less like that. And once again, we can see that the areas of the two pieces, the area of the piece that's above the x-axis and the area of the piece that's below the x-axis, are roughly equal, but they're opposite in sign. So once again, we should see that, and I didn't write down the function here, but we should see that from 0 to L, sine of pi x over L times sine of 2 pi x over L dx should equal 0, because these areas will cancel each other out. So that's the bottom line for what's going on here. Now, I should say a few words about what to look for sometimes in this. If we have functions that are centered around the origin, and the integration limits are equally distributed across the origin, so it basically goes from a minus a to an a, or a minus infinity to infinity, we may care about the symmetry of these functions as to whether they are even or odd. And so I want to define those for you. If I have a function that is equal to itself when it's at a negative x value, this is a definition of what we would call an even function. On the other hand, if I have a function that changes sign when I go to the negative side, this is something that we would call an odd function. So when I multiply two functions together, if they're both even, I would get an even result at the end. If they are both odd, I would also get an even result. The only time I don't get an even result is when I multiply an even times an odd. An even times an odd will give me an odd function. All right, so what does that mean? Well, what I've drawn here are some odd functions, not odd in the sense of being strange, but odd in the sense that they have this property. And when they have this property and my integration limits are equally distributed about the origin, then I'm going to end up with 0 as my result. So this is one way you can quickly determine if something is going to give you orthogonal functions or not. If one function is even and the other is odd, then most likely almost certainly they're going to be orthogonal to one another, and they're going to show a 0 for this kind of integral.